For the limit statement, the limit as x goes to c of the function f of x equals L, we can write out a formal statement that would describe what this limit is. And that statement here we can complete by filling in the blanks. So we say that the limit means that for all epsilon greater than 0, so that little script E looking symbol is called epsilon. So we say for all epsilon greater than 0, there exists delta greater than 0. So delta almost looks like a little S where there's a little loop there at the bottom. And that's what we're calling delta. So we say for all epsilon greater than 0, there exists delta greater than 0, such that if, and we've got to tell in this blank where the x is living. So we say such that if x, and then that symbol is in or is an element of the following set. So we say that if x is in, and this is going to be the punctured interval, it's c minus a little bit, so c minus delta to c. And then we have the union symbol that says c to c plus a little bit, the c plus delta. So this here is going to be our punctured interval. It's really on the number line, what it looks like is we've got this c value here in the middle, the value that x is approaching. So if we're going a little bit below it, the c minus delta, and a little bit above it, c plus delta, we really have this whole interval that goes from a little bit to the left of c to a little bit to the right of c, but we don't want to include what's happening exactly at c. And so all of that notation that you see in the blank there, x is in this punctured interval, is really just saying the interval that is symmetric around c, but doesn't include c. We don't want it to tell us what's happening exactly at c, just nearby on both sides of c. Okay, so we have such that if x is in this punctured interval, we want to show where, or we want to be able to explain where the function is going to be and how close it would be to the limit value. So what we would then have is that the function f of x would be an element of basically just a symmetric interval around or within this symmetric interval around the limit value. So it would be L minus a little bit, so the L minus epsilon, to the L plus a little bit, which would be the L plus epsilon. So that would be the formal statement for the limit. And what that looks like pictorially here is this formal statement starts with for all epsilon greater than 0. So in general, you'll have some epsilon value that tells you how far to go away from the L, how far to go above and below the L. So we would have like an L plus a little bit and an L minus a little bit there. So then what happens here is we can take this these y values there, the L plus a little and L minus a little, trace it to the function, and then bounce down to the x-axis to see what x value there would be on the barrier that would trace back to the L plus epsilon y value. And then we do this also for the L minus epsilon. So here we would trace over from the L minus epsilon y value, bounce down to see the x value that would correspond to it. So now notice that the intervals for both x and for the f of x are really symmetric intervals around c and L. And so notice here on the x-axis we have two x values that aren't symmetric around the c. So we've got the big distance, and by big it's not that big, but it's the bigger one, and then we've got the smaller one. And so what we have to do then to get this symmetric interval is the distance that was the smaller distance is what we then choose as our delta. So this is going to give us our delta so that we can now have that symmetric interval. And see what's going to happen then is here on the left-hand side, it did not go all the way out to the x value that we got when we traced backwards there. But notice that if by sticking into the smaller range, we have this vertical bar of all the x values that land there, that we could trace back to this horizontal bar that would be a subset of our original horizontal bar that we started with. So that's why we've got to always go there with the smaller distance on the x-axis so that we can trace back and make sure that we do land in the right place for the y-axis. And so this is our formal definition with a sort of pictorial sense of what that would look like in just kind of a standard limit situation. But then we do have this idea of one-sided limits that we could also have formal definitions for, and rather than writing these out completely, since they're very similar to the original just two-sided limit, I just want to show you what's different about it, or explain to you what's different about it rather than starting from scratch as if it's a new concept, because it's not. So the two-sided limit had to take into account what was happening both to the left and to the right of C in the whole situation. But see, the left-hand limit would only take into consideration what's happening to the left of C. So really what we're going to be doing then is the only change that happens here when we're looking at a left or right limit versus an entire limit happens in this x interval here that we have, the interval of x values. So if we're talking about a left limit, we're really talking x is in only the left part, so the part that is C minus a little bit to C, and then we don't worry about the right-hand part. Of course, for the right-hand part, we worry about the right but not the left. So it would be the x in the right-hand part would be the C to C plus a little bit. So the C plus delta part. So the only change that you would need to make when you're only considering a one-sided limit was instead of the entire punctured interval of x values, you just pick either the left part of that punctured interval or the right part of that punctured interval. And you've got your formal definition for the one-sided limits as well.